So here's an activity that I would normally do in groups if we were in the classroom. So this is a real world application of limits. The population of bears in a certain region is given in the graph of P below. And we have time along the bottom. So time is measured in months. So we have like parts of a month. And then along the vertical axis is our bear population. So that's of course in whole numbers of bears. So we're going to take a look at some limits here. We're going to look from the left, from the right, blah, blah, blah. Take a look at that. So we'll start with A. So all of these are what the population is at some time. So 0.6 coming in from the left-hand side. So we find 0.6 down here. And then coming in on the left-hand side. So what we're going to see here, notice, is that because we're only coming in from the left-hand side, and we do have a value leading all the way up there, even though we don't have a value at 0.6, that's okay. Our answer here would still be 33. So what it's telling us is that the bear population is 33 bears up until 0.6, but infinitely close to 0.6. At the moment that time passes and we're at 0.6 of a month, then the population of bears changes. Looking at B, we're looking at what happens when we come from the right. So very similar. Again, it doesn't matter that there's actually a value there at the 0.6. What matters is that we have this line that continues on and gets closer and closer up until 0.6, and that is 34. So notice that on either side of 0.6 of a month, we have a change in the number of bears. So when it asks C, it asks, well, what is then the limit as time approaches 0.6? Well, that's an issue because we don't have the same population coming in from the left-hand side and the right-hand side. So in this case, we are going to have a does not exist there. The limit does not exist because it's not the same on the left and the right. We'll take a look similarly to 0.8. So coming in on the left at 0.8 for D. Looks like we actually have 35 coming in on the left there. And then coming in on the right, we can see just 34. So notice that as certain time is passing, like there is a change in the number of bears. Similarly, like looking at the limit as t approaches 0.8, there's just a problem because those are not equal. One's 35 and one's 34 coming in from each side. So we have another does not exist. I typically put like kind of an arrow thing just because it's not equal to does not exist, it just does not exist. So for part G, where it says explain what events might account for the points at which no limit exists, in that case, we really just want to be thinking about the fact that this is essentially what's called a step function because it has these jumps in it. And so there's, a value and then the next value is really low or high, depending on how much it's going up or down. But when it asks explain what events, we just want to think about the fact that if we're talking about the population of bears and the population of bears is going up and down, it's because sometimes bears are born and sometimes bears die, but you can't have like a part of a bear. And so if you're talking about such a discrete number of bears here, just from 30 to 35, we have to jump, right? Because we're not going to be talking about like a part of a bear. So there's either 31 bears or there's 32 or there's 35 like that. So now to finish this section up, we are going to graph and fill in each blank so that we have limits that exist. For both of these examples, the limit is at 2, meaning that it's piecewise functions where we have pieces on either side of the value x being 2. So what I've done is I've drawn these little like dotted lines that go vertically just to remind myself, okay, half of this function is on one side and half is on the other. If you want, you can work on the first problem with me and then try to do the second problem by yourself. They're very similar, just with slightly different functions. So for the first one, we have 2 pieces. We have piece 1, piece 2. Notice that piece 2 is complete. It is a linear function. It is negative x plus 6, and that is for anything greater than 2. Now, because it's a line, I know that it continuous and it just keeps going in either direction along the whole plane. So I want to graph this for anything greater than 2, but I also know that greater than 2 means it could be 2.000000001. And so because of that, it becomes where at 2, we just know we're going to have a hole. So if we plug in 2 to this function, negative 2 plus 6 is a positive 4, it's telling me that this line has a hole at 4, but then I could put in x being 3, and I'll get 3, and I could put in x being 4, and I'll get 2, and it's going to go like that. So I'll go like this. And this is what this piece of this piecewise function looks like. So what we want is we want the other piece, which you can see is also a line, just missing essentially its y-intercept, it's constant. We want that to meet up with this line, because then we have a limit that exists, and then we're approaching that value from both sides. So we need the point, as you can see, 2, 4 to be part of that graph. So what we can do then is say, okay, since that second piece is linear, I'm going to write it like this. I'm going to call the blank thing B, but we need it to be include that point. So we need that y is at 4 and x is 2. And you can see just by doing a couple steps here that we get b equals 3. So that tells us that our blank is 3. And this is a line with slope of 1/2 and y-intercept 3. So if we do y-intercept being 3, and then we do a slope of 1/2, that's up 1 and over 2. And there we are. And that is on that line because it's less than when x is less than or equal to 2. So that also is included. And we can go down 1 and over 2 and like that. And then we just have our other line that is a little bit different than the first one and looks like that. But now we have a limit that exists for x equal 2 as x approaches 2. We do have a limit now of 4. Coming over to the other one, it would be very, very similar. Obviously, we do see that we have quadratics now. We see that we have piece number 1 complete and piece number 2 has the blank. So piece number 1 is x squared minus 9. That's a quadratic, and that's for anything less than or equal to 2. So since it's equal to 2, if I plug in 2 to that piece and I take 2 and I square it, and I subtract 9, I get negative 5. So that first piece has the point 2, negative 5 on it. If we plug in 1 to that first piece, you can see that we would get negative 8. If we plug in 0, we get negative 9. And then hopefully you should see that there's some symmetry going on here because of where the vertex is. So the first function is going to look like this. Let me go down a little bit lower. I'm at the bottom of my tablet, but there we are, something like that. So now we need our other quadratic to just be on the other side. And notice that it faces downward because it's a negative x squared plus some value. So very similarly to the last one, we have this point 2, negative 5, and we want this other function to meet up at 2, negative 5. So if we write this out as y equals negative x squared plus b, b being what that value we're looking for the blank, and we know we have that 2, negative 5 that we want it to meet, well, it needs to have that point. So we can do negative 5 here, we have a negative and then 2 squared plus b. So you're going to have a negative 2 squared, that's 4, times negative 1 is negative 4. So we're going to take that negative 4, we're going to add it to the other side, so negative 5 plus 4 is a negative 1. So we get our value, negative 1. And really, in order to graph this, you just pick some values. So we already know that it's going to meet up at the 2, negative 5, because that's how we found b. But if we put in 3, you can see that if we did 3 squared, that's 9, times negative is negative 9, plus a negative 1 is a negative 10. So we have this point down here. And then, we can do other points. They're just not going to be something that's part of it because we want to be on the right side of 2. So we do know that it has a y-intercept of 0, negative 1. So we know that it comes down. So we can just kind of keep it going down like this. But the important thing to see is that now a limit exists because the graph is heading towards 2 on either side, and both of those sides are approaching negative 5. So now we have our answer.